Now that we've looked at the scale factor of linear lengths, we're going to see how we can expand that to talk about how we can scale up area and scale up volume. So first, let's take this regular rectangle and let's work with what we've already learned. If I am dealing with a rectangle that has dimensions of 3 centimeters by 4 centimeters. So basic, we are just thinking about that area being length times width. Right, so when I'm looking at the dimensions of 3 by 4, my area is 3 times 4. Right, so I have an area of 12. Keeping in mind my units is centimeters squared. If I have a linear scale factor of 2, right, that means that not only is my width going to get twice as big, my length is also going to get twice as big. Right, so if I'm saying my linear scale factor, if I'm saying this whole thing in each linear direction, right, one-dimensional direction, is getting 2 times bigger, right, my length was 3 becomes 6, and my width was 4 is going to become 8. So notice that when I find that new area and I actually do 6 times 8, I get 48 centimeters squared. So if I'm going from 12 centimeters squared to 48 centimeters squared, I have more than a scale factor of 2. It's doing more than doubling. And again, I can find that scale factor, same way that I did with linear, by taking my new measurement, my scale, divided by my original. And I get an area scale factor, so a 2-dimensional scale factor of 4. Which means that even though each length is only increasing by a factor of 2, the area is increasing by a factor of 4. I have 4 times as much area as I started with. In another rectangle, so if I'm starting with something 2 by 4, right, I have an area of 8 centimeters squared. If my linear scale factor is 0.5, right, each distance, each length, each linear measurement is going to be half as long. So I'm looking at 1 by 2. My new area, if I do 1 times 2, is only 2 centimeters squared. Right? And so even though I'm having that linear measurement, right, to 0.5 for each of those 2 sides, when I think about taking my new measurement divided by my original measurement, turns out I'm actually getting a quarter of the area. We'll look at a couple more really quick. If my dimensions are 5 by 3, right, I have a 15 centimeter square area. If I triple each length, I'm looking at something that's 15 by 9. When I go ahead and do 15 times 9, I'm going to get 135. Oh, magical color change, 135 centimeters squared. If I'm thinking about my area scale factor, again, that scale factor formula is still the same. It's still that new value divided by old, right? Or diagram divided by original or actual. And so I do 135 divided by 15, and I get 9. We'll do one more, then we'll see if we can recognize the pattern. 9 by 3, 27 centimeters squared. If I'm scaling back by a third, so each length is 1/3 as long, I have something that's 3 by 1. I go down to only having an area of 3. Again, looking at that scale factor, 3 divided by 27, well, that's reduced down to 1/9. So how am I getting from these linear scale factors to these area scale factors? Are we seeing a pattern between how does 2 turn into 4? And how does 0.5 or 1/2 turn into 1/4? How does 3 turn into 9? And how does 1/3 turn into 1/9? Well, what we're doing to get from that linear scale factor to that area scale factor, because we're seeing that linear value happen in multiple directions, right? Multiple dimensions. I'm scaling up by 2 in my length, but I'm also scaling up by 2 in my width. What happens is that I'm actually squaring that linear scale factor. Right? 2 squared gives me 4. 1/2 squared gives me 1/4, right? If you square a fraction, it becomes an even smaller fraction. 3 squared gives me 9, and 1/3 squared gives me 1/9. So my area scale factor is my linear scale factor squared. So that way I can bypass needing to know the length and the width, needing to even do an area calculation, if I can jump straight from my linear scale factor to my area scale factor. So let's see some of the questions that we'll see on this sort of topic. So the right triangular prism has a surface area of 42 meters, right? When we're thinking of surface area, that's actually a unit squared. My bad on the typo, right? Surface area is a 2-dimensional measurement. If the given prism increases in size by a scale factor of 3, what will the surface area of the new prism be? All right, so when they say scale factor, if there's nothing that is necessarily implied, we assume linear scale factor. Right? It'll usually be pretty clear in the question. So let's say that, right, the height of the prism, or right, every dimension of the prism increases by a scale factor of 3. Because we're now working in 2 dimensions, I can't just triple my area and call it good, because I'm actually increasing by a scale factor of 3 in more than 1 dimension. So if I'm seeing something about area, we have our usual formula, right? Scale over actual, right? Scale or diagram over actual diagram is equal to my scale factor. If I want to talk about the scale factor or the scale diagram or the actual diagram, if I want to talk about any of those in 2 dimensions, so specifically in this case, my actual diagram or my original shape is in meters squared, is an area. I want to make sure that all 3 things, the same dimension. Right, so if I'm saying that the actual is area, then I need to find the scale value in area, which will be my new surface area, which means I need to be working with an area scale factor. So my linear scale factor is 3, which means that when I square that, when I think about increasing that in multiple dimensions, in 2 dimensions at once, my area scale factor is 3 squared is 9. So when I go to plug in values into my formula, right, where x is my new scale surface area, right, my scale diagram, my original was 42. I want to make sure I'm including that area scale factor of 9 so that I can say all 3 of these portions of this equation are talking about an area. They're talking in 2 dimensions. But I solve it the same way that I did before. I can multiply up this 42, and I can find out that x is 378 meters squared. Right, so while the linear dimensions tripled, the area, or the surface area, actually was raised times 9. So 378 meters squared is my new surface area. Let's look at another one. If a room's dimensions, and when we say that, right, room's dimensions, we're talking about length, we're talking about width, we're talking about individual linear measurements. So if my room's dimensions are increased by a scale factor of 4, right, that's our hint to tell us that this, again, is our linear scale factor of 4. And the room started with an area of 27 meters. What is the area of the new room?